Okay, I quick want to, as opposed to doing a checkpoint, I quick want to refresh your memory from yesterday, and we were trying to approximate the square root of 6, right? And right, so I just want to make sure that we see how we kind of come up with this piece. So, Sean, what was your first guess? Do you remember? 3. So his first guess was 3, and let's just roll through this real quick. But you remember, you need a function. What's the function? Yeah, and then f prime of x is 2x. So Newton's equation says x minus f of x over f prime of x will give us our new guess, right? So, you're able to take 3 minus, when you plug 3 in, 3 squared, 9 minus 6 is 3, over 2 times 3 is 6. So 3 minus 1/2 is 5 halves in, right? So 3 was our first guess. 5 halves will be our second guess. If we take that 5 halves and we minus 5 halves squared minus 6 over 2 times 5 halves. So let's work this out, and we're going to do it one more time so you can see how great of an approximation it is. 5 over 2 minus, what's 5 halves squared? 25 over 4 minus 24 over 4 over 5 over 1. And I get 5 halves minus, look at what happens to this part right here. You get a small value, don't you? And as you continue to move along, that top piece is really how much error you have. We get 1/4. That's what our error has turned out to be. So it's smaller. Divided by 5 over 1 or multiplied by 1 over 5. And you can see it now becomes even smaller. We get 5 halves minus 1/20. Or if you multiply by 10, we get 49 over 20. Well, so we'll call this Jake's number, okay? We'll give it a special title, Jake's number. And suppose that Jake's number wasn't, I guess, good enough for Newton, okay? So, well, you're right, can't please everybody. So you can see 3 squared, not very good, but 5 halves, 5 divided by 2, if we square that, closer to 6, but still off by 1/4. And then all of a sudden, Jake comes forth, the great mathematician, and puts forth 49/20 and squares it. Now, you can decide, if that's really sufficient for you. But suppose it wasn't. Let's just carry it out once more. Well, I think you're going to be satisfied once you see the next process. So 49 over 20 minus 49 over 20 squared minus 6 over 2 times 49 over 20. 49 squared is 2,401 over 400 minus, I have to write 6 with a denominator of 400. What's 6 times 400? 2,400. So look at what happens to that. What does that fraction turn out to be? So that's your error. It's very small, 1/400th. Divided by 2 times that will be 49 over 10, and we will go to work. We are almost there. 49 over 20 minus 1 over 400 times 10 over 49. You can see that one of those will cancel. 40 times 49. 1 over 1,960. Find common denominators. Multiply top and bottom by 98. And I get, that one I don't know. Didn't remember that. 98 times 49. 4,802 minus 1 over 1,960. And we get 4,801 over 1,960. And we will call this Sean's number. And so 4,801 divided by 1,960, and if you take that and square it, wow. I mean, You're ridiculously close there. And if you want to actually see what the actual square root of 6 value is, take the square root of 6 and compare that to 4,801 divided by 1960. Now, again, we're not going to try to duplicate this a lot, but look at the difference here. It's remarkably close. I think that that's rather impressive, that you come up with a rational number that is approximately equal to the square root of 6, and it's pretty close. So that's sweet. No, I'm just saying that understand what Newton would do. And if he wasn't satisfied with 49 over 20, do it once more. And what an amazing approximation that is. So let's pick up with our notes. Open your notes and flip to this portion. And we're going to look at some graphical pieces of Newton's method. It's so important that you understand what happens graphically with this approach. Yesterday we focused on the formula. So first I'm going to plot a few points. 1, 2, 3, 4, 5, 6. And you're going to draw this graph. You're going to put a dot down here so it has an x value of 2, and then a dot up here so it has an x value of 4, and a dot then at 3. And the graph we're going to make is going to look like this. We just have these 2 short examples today. You should have the full time after lunch to be able to work, okay? And we'll talk about the schedule for the rest of the week and what we're going to be doing. In order for you to understand graphically what's happening, we have to kind of refresh our brains of where we started yesterday. Does everybody have this down? So here's what Newton's method did. We had a value. So that's 2 and that's 3. We made 3 a guess. And once we made 3 a guess, we found a point on the curve. What did we then do? We drew a line tangent. And what part of that line did we try to find? The x-intercept. The x-intercept of that line is actually very close to the actual value, correct? And then if we weren't satisfied with that, we did it again. We found another point and we drew the line tangent. And you notice how quickly you can arrive to a value that's very close to the actual x-intercept. So let's apply the same method to this. And what Newton would say is, he'd say, hey, I want to find the actual x-intercepts of this graph. Where does the x-intercept occur on this graph? 3. Well, suppose he was carrying out his method, and suppose his first guess was not 3, not 2, not 1, not 4, but it was 0. If he guesses 0, watch what happens. He finds a point on that curve. What should he then do? Draw a line tangent. Once he draws the line tangent, what spot on the line does he want to find? Did that draw me closer to the x-intercept or further away? Drew me further away. So you're like, well, maybe if I do it again, it'll work out better. So you try it again. Oh, no. And then you try it again, and you realize, oh, my goodness, the x values are drawing you all the way out towards negative infinity. So that's not going to give you the x-intercept. So for that reason, it's important to have a good guess. And we're going to talk today about how to find a good guess. Suppose I guess 1. I draw the tangent line. Is that going to change anything? I'm still going to head out towards negative infinity. Suppose I guess 3. What's going to happen? You're going to be right, aren't you? You're going to come up, when you plug it in, f of 3, you're going to get 0, right? And so you're going to get 3 as the answer. X is equal to 3, okay? What if I guessed 4. I draw a line tangent, and what do you notice about this tangent line? It never crosses the x-axis. So you're not going to come up with a result. You got nothing. Because you'll actually remember what you'll come up with an undefined value, because remember, Newton's method says you take x minus f of x over f prime. Well, what is f prime of x in this situation? What's f prime right here? So you'll be dividing by 0. Can't do that. What if you guess 5? Yeah, you're going to then guess here, and it's going to draw you out towards positive infinity. So it's important to have a good general guess to begin with. Can somebody out there tell me what is a good guess to begin with? Or, I'm sorry, what is the window in which I should be guessing if I want to come up with 3? Greater than 2, less than 4. If I guess somewhere between 2 and 4, hopefully I'll come up with it. Now, that might not be exact because we do have some issues. For example, if I guess really close to this spot right here, I guess really close to 4, you might end up out here and then having issues. But at least that's a reasonable idea to guess between those values. Okay. All right. So what if Newton encountered this type of a problem? So yesterday we talked about estimating the square root of 5. What if he wanted to find the actual solutions to that polynomial, meaning all 3 roots? Now, this is a cubic. I told you guys about the cubic, and that was, about Tartaglia solving it. But, suppose we didn't have any of that information, and we wanted to try to find where it crossed the x-axis. If you were asked to find the x-intercepts of that, and you were able to look at the graph, what would you do using your calculator to find one of the x-intercepts? You'd calculate a 0, right? What? Well, do it by hand using Newton's method, but watch what happens here. It's asking for a left bound. What did we do? We gave a boundary, didn't we? And your calculator is using a version of Newton's method. And then you move to the right, and then what does it ask us for? A guess, to make sure that we're in a good spot. So you can move it so that you're close, and it finds it, negative 1.525687. So what we're going to do is we are going to find those x-intercepts, except we're not going to use the 0 method. We're going to use Newton's method, and we will use our calculator for assistance. But here's the idea. I'm going to take this, and I'm going to find these 2 points. I believe that these 2 points are probably pretty important. Would you agree? How do I find those 2 spots on my graph? I set the derivative equal to 0. What is the derivative of that function? So I have 3x squared minus 2. If I add the 2, I get 2 is equal to 3x squared. Divide by 3. So x is equal to plus or minus the root of 2/3. And for this application, we will leave, we won't rationalize the denominator. We'll just write it as negative root of 2/3 and positive root of 2/3. So if I would like to use Newton's method to find this, I have to take x minus f of x over f prime of x. So the rule I want to use is x minus, what is the function? X to the third minus 2x plus 1/2. And what is the derivative? 3x squared minus 2. Well, let's take that and let's plug it into our calculator. Got to use my parentheses. I'm going to go to my table. Looking at your graph, if I want to estimate this x-intercept right here, can you tell me what would be a bad first guess? -7 is a little bit far away, but I would still end up getting there. It would take a while. 0 would be a horrible guess. I will never arrive at the right spot if I guess 0 right away. So what would be a reasonable guess? -1, -2. Let's try -1. So I try -1, and I get -2.5. What should I then do with that? Plug it back in, -2.5. What do I do that? -1.896. Again, we are not doing the arithmetic, but we are doing Newton's method. And that was what we came up with when we did the problem originally, right? -1.526. Somebody give me what I should guess for the second one. I think 0 would be an excellent guess. 0 is obviously going to give me 0.5 or 0.25. Oh, yeah. Because I'm not plugging in the function, I'm then dividing by a derivative. My bad. Okay, then we plug in 0.25. Because we want a value between -√2/3 and +√2/3, and we don't want to get too close to them. So we try something in the middle. 0.25862 and 0.25865, and it looks like that's it. 0.25865. Anybody want to suggest what I should guess for my last one? If we guess 1, 1.3, 158, 1.2, 699, 1.267, 1.267. And if we did the second calculate option on our calculator, we would sure enough come up with those 3 values. So that's a little bit about how your calculator can operate. Now there's different recursive formulas that they can use, but that's one. Not everybody gets sleep every night. It's okay. All right, so what do I have for you? I have an assignment. You're going to have the rest of the time in class to work on it. You have a full work day tomorrow. On Monday, we will review for the AP exam by doing some good multiple choice problems from Section 3 and Section 4. On Tuesday, you will have your study guide day. I will get to you a study guide tomorrow. And then your test is on Wednesday.